Hello, and welcome to Midnight Space, where we embark on a journey to the cosmos, one that's as vast as the universe itself and just as mysterious. If you're new here, be sure to like and subscribe to stay up to date with all our explorations into the wonders of space. And while you're at it, let us know where you're watching or listening from. Whether you're tuning in from Earth, or perhaps imagining yourself in the depths of space, it's amazing to think about how we're all connected across time and space, just like the very gravitational waves we'll be exploring today. Gravitational waves, ripples in space-time that travel across the universe, have opened up a new frontier in our understanding of the cosmos. They carry the echoes of some of the most violent, yet invisible events in the universe, events that are often millions or even billions of light-years away. But what are gravitational waves? How do they form? And what can they tell us about the universe we call home? Tonight we'll be exploring all of that and more. Buckle up as we journey through space-time itself and dive into the fascinating world of gravitational waves. Let's begin. Gravity. It's something we all experience every day. It keeps our feet on the ground, makes things fall, and shapes the very structure of our universe. But what if gravity isn't just a force that pulls objects toward each other, as we might think? What if it's something far more intricate, something woven into the fabric of space itself? The concept of gravity has been with us for centuries, ever since Sir Isaac Newton first proposed that objects fall toward the Earth because of an invisible force pulling them downward. This idea revolutionized how we understood the universe, offering a simple explanation for why things fall and why the planets orbit the Sun. But even Newton, as brilliant as he was, didn't have the full picture. It wasn't until Albert Einstein's theory of general relativity in 1915 that we began to truly understand the deeper nature of gravity. Einstein showed us that gravity isn't a force in the traditional sense at all. Instead, it's the result of the curvature of space-time, the four-dimensional fabric of the universe that combines space and time into one unified continuum. Objects like the Earth or the Sun create dents or curves in this fabric, and these curves are what cause the movement we call gravity. Picture it like a heavy ball sitting on a trampoline. Its weight causes the fabric of the trampoline to sag, and this causes smaller objects like marbles to roll toward the ball. But what happens when these objects move in such a way that they don't just affect the nearby space-time, but send ripples through the entire fabric? That's where gravitational waves come in. Gravitational waves are essentially ripples in space-time itself, created by the acceleration of massive objects. These waves travel outward, carrying energy and information about the source of their creation. Just like the ripples on the surface of a pond when you throw a stone, gravitational waves spread across the universe, stretching and compressing space-time as they go. It's easy to confuse gravitational waves with gravity itself, but they are distinctly different. Gravity is a constant force. It's the reason we stay grounded, and it shapes the orbits of the planets. Gravitational waves, on the other hand, are dynamic, temporary distortions in space-time that occur only when massive objects accelerate or collide in specific ways. It's a subtle but important distinction. Gravity is the fabric of the universe. Gravitational waves are the waves that ripple through it when something shakes it up. To better understand gravitational waves, it helps to think of the universe as a great cosmic dance. Planets, stars, black holes, and even light all move in this cosmic symphony, influencing one another with forces like gravity. When two massive objects, such as black holes, collide, they send shockwaves through the fabric of space-time, gravitational waves, across vast distances. These waves, while incredibly faint by the time they reach us, hold the key to understanding some of the most extreme events in the universe. But while Einstein predicted gravitational waves in his general theory of relativity, he didn't know whether they would ever be detectable. After all, these waves are incredibly weak by the time they reach Earth. In fact, the stretching and compressing of space-time is so subtle that you'd need incredibly sensitive instruments to detect them. And this is where the work of scientists and engineers comes into play. Though Einstein's theory was published over a century ago, the search for gravitational waves didn't truly begin until much later. It wasn't until the 1960s and 70s that scientists like Joseph Weber and others started building experimental detectors to look for these elusive waves. Weber's early attempts were a precursor to the groundbreaking work that would follow, but it wasn't until the development of the Laser Interferometer Gravitational Wave Observatory, or LIGO, that we had the technology capable of detecting them in earnest. But how do you even detect something as faint as a gravitational wave? Imagine, for a moment, that you're trying to measure the length of a piece of string. Now imagine that the string is being stretched and compressed by a fraction of the thickness of a human hair, all the way across a distance as long as a football field. That's how sensitive LIGO's instruments are. They measure the incredibly tiny distortions in space-time that occur when a gravitational wave passes by. This technology is what made the impossible possible. After decades of research and a lot of skepticism, in September of 2015, LIGO finally detected its first gravitational wave, a signal from a collision between two black holes, located about 1.3 billion light-years away from Earth. It was a monumental moment in physics, confirming Einstein's predictions and opening up a whole new way of observing the universe. But the detection of gravitational waves didn't just confirm Einstein's theories, it also marked the dawn of a new era in astronomy. Unlike traditional telescopes, which rely on light to observe distant objects, gravitational wave detectors allow us to hear the universe in a completely different way. Instead of seeing the light emitted by distant stars and galaxies, we're able to listen for the vibrations of space-time itself. It's as if we've been looking at the universe with blinders on, only now are we able to remove them and hear the hidden symphony of the cosmos. Before this discovery, the universe seemed silent, even though we knew there were extreme events happening out there, black holes colliding, neutron stars merging. There was no way for us to detect them directly. Gravitational waves changed that. Now, we can listen to the sounds of these cosmic events, even if they happened billions of years ago. This discovery also brought a renewed interest in the minds behind these ideas. People like Karl Schwarzschild, who, in the early 20th century, developed the first exact solution to Einstein's equations describing black holes. Schwarzschild's work helped shape the understanding of space-time curvature and the mysterious properties of black holes. Though not as well known as some of his contemporaries, Schwarzschild's contributions laid the very foundation for the theories that would lead to the detection of gravitational waves. And so, the excitement of discovery continues. With each new detection, we learn more about the universe's deepest secrets. As scientists continue to refine their instruments and expand their reach, there's no telling what we'll discover next. Perhaps we'll hear the remnants of the Big Bang itself, or catch the faintest signals of other dimensions. Whatever comes next, one thing is certain. Gravitational waves have forever changed the way we explore the universe. Albert Einstein's theory of general relativity, published in 1915, was a radical departure from the conventional understanding of gravity. For centuries, scientists had believed that gravity was a force that pulled objects towards one another. But Einstein showed us that gravity is much more than a force. It's a manifestation of the curvature of space-time itself, caused by the presence of mass and energy. This idea revolutionized the way we thought about the universe, offering a new, profound understanding of how planets, stars, and even light move and interact. One of the most exciting implications of general relativity was the prediction of gravitational waves. According to Einstein's equations, massive objects like stars and black holes create ripples in the fabric of space-time when they move or collide. These ripples travel outward at the speed of light, carrying energy and information across the cosmos. Gravitational waves were, in a sense, the sound of space-time being disturbed by the motion of massive objects. These waves were predicted to be incredibly faint by the time they reached Earth, but they should still be detectable if we could build the right instruments. But even with this groundbreaking prediction, the scientific community was initially skeptical. Einstein himself had doubts about whether these waves could ever be observed. In fact, for much of the early 20th century, the idea of gravitational waves seemed more like a theoretical curiosity than a practical reality. At that time, physicists were still grappling with the implications of general relativity, and the tools needed to detect gravitational waves were nowhere near ready. Despite this, there were a few forward-thinking physicists who recognized the importance of gravitational waves and began to explore the possibilities. One such physicist was David Hilbert, a German mathematician whose work complemented Einstein's theory of general relativity. In fact, Hilbert and Einstein were working on the same set of equations almost simultaneously, each arriving at similar conclusions. However, while Einstein focused more on the geometric nature of space-time, Hilbert's work explored different formulations of the equations, attempting to approach the problem from a slightly different angle. Some of Hilbert's early insights helped refine the mathematics of general relativity and provided a solid foundation for understanding how gravitational waves might behave. But there were also alternative theories of gravity that challenged Einstein's view. One of the most notable was proposed by Theodor Kaluza, a German theoretical physicist in the 1920s. Kaluza, in a daring move, combined general relativity with electromagnetism into a single unified theory. His idea was based on the notion of extra dimensions, dimensions beyond the familiar three of space and one of time. He suggested that gravity and electromagnetism could both be manifestations of a higher dimensional spacetime. Though Kaluza's theory didn't gain widespread acceptance at the time, it laid the groundwork for later developments in theoretical physics, including string theory, which would eventually propose even more dimensions, up to 10 or 11, hidden from our everyday experience. Kaluza's ideas, although not immediately influential, would be revisited decades later as physicists sought to unify the forces of nature. His work inspired later efforts to incorporate additional dimensions into our understanding of the universe, something that is now central to modern theories like string theory. These theories suggest that gravitational waves might not only reveal information about our own four-dimensional spacetime, but could also offer hints about the nature of these extra dimensions, which remain hidden from direct observation. In a sense, Kaluza's early work on extra dimensions was an example of how even unconventional ideas can spark future discoveries. Another physicist who played a key role in advancing our understanding of gravitational waves, though often overlooked, was Roger Penrose. Penrose's work on black holes in the 1960s fundamentally changed our understanding of the most mysterious objects in the universe. He demonstrated through his concept of the singularity that black holes contain regions of spacetime where the gravitational field becomes infinitely strong and the curvature of spacetime becomes infinitely steep. These singularities, however, were not part of Einstein's original theory, and Penrose's work opened up new possibilities for understanding the deepest mysteries of general relativity. Penrose's ideas also helped shape the way we think about gravitational waves in relation to black holes. According to his work, when two black holes collide, they form a singularity, a region of spacetime where our usual understanding of physics breaks down. The collision itself would create intense ripples in spacetime, known as gravitational waves, that we could detect. These waves would carry information about the black holes involved, including their masses, spins, and the geometry of their merger, and it was Penrose's work that helped point to the importance of these waves in revealing the hidden nature of black holes. Despite the theoretical work done by these scientists, the detection of gravitational waves remained elusive for many decades. The first hints of gravitational waves came in the form of indirect evidence. For instance, in the 1970s, scientists like Joseph Taylor and Russell Hulse discovered a pair of neutron stars orbiting each other in a binary system. Over time, they observed that the orbit was shrinking, and the stars were losing energy. This was a key prediction of general relativity, the loss of energy through the emission of gravitational waves. The fact that the stars were losing energy exactly as Einstein had predicted was indirect evidence that gravitational waves were real, but it would still take several more decades before we could directly observe them. As the 20th century wore on, the idea of gravitational waves moved from a theoretical curiosity to a subject of serious scientific investigation. In the 1990s, scientists began building large-scale detectors, like LIGO, to try to measure these faint signals. But despite all the effort, the technology needed to detect such weak waves was still in its infancy. It wasn't until the 21st century that technological advances, along with decades of theoretical groundwork, finally brought us to the point where we could make the groundbreaking detection of gravitational waves in 2015. That discovery was a triumph not only for the scientists at LIGO but for the entire field of physics. It confirmed Einstein's 100-year-old prediction and opened the door to a new era of astrophysical exploration. Gravitational waves have allowed us to hear the universe in ways we never could before, listening to the collision of black holes, the merger of neutron stars, and the violent events that shape the very structure of space-time. As we continue to explore the universe, the theory of gravitational waves will undoubtedly lead to more discoveries, more breakthroughs, and more questions. We've only just begun to scratch the surface of what gravitational waves can tell us about the most extreme and mysterious events in the cosmos. And who knows what we'll discover next? Perhaps gravitational waves will one day help us answer some of the biggest questions in physics, like the nature of dark matter, or even the mysteries of the Big Bang itself. But for now, the discovery of gravitational waves remains one of the most exciting achievements in the history of science. While the names Kip Thorne and Barry Barish are often associated with the landmark detection of gravitational waves, the discovery of these cosmic ripples was the result of the combined efforts of many scientists over decades, some of whom have become iconic figures in the field, while others remain more obscure even though their contributions were just as vital. One such key figure is Jocelyn Bell Burnell, whose discovery of pulsars in 1967 paved the way for understanding some of the most intriguing sources of gravitational waves. Bell Burnell was a young graduate student working with Anthony Hewish at the University of Cambridge when she noticed a peculiar, repetitive signal coming from a radio telescope. This signal turned out to be a previously unknown type of star, later named a pulsar, which emits regular bursts of radio waves. Pulsars are a kind of neutron star, dense remnants of supernova explosions that spin rapidly and emit beams of radiation. While this discovery didn't directly involve gravitational waves, it gave scientists a crucial new tool to study the universe's most extreme objects. Pulsars became a key piece in the puzzle of gravitational wave detection because many of them exist in binary systems, where two stars orbit each other closely. When such systems are made up of neutron stars or black holes, the system is capable of producing gravitational waves, much like a pair of spinning ballerinas twirling in the center of a cosmic stage. Bell Burnell's discovery not only opened up a new branch of astrophysics, but also provided researchers with a practical way to indirectly detect gravitational waves. For instance, the timing of pulsar signals can reveal subtle changes in the motion of binary systems, helping astronomers detect the effects of gravitational radiation. Though the idea of gravitational waves was still theoretical at this time, Bell Burnell's pulsar discovery helped shift the focus toward these exotic objects and set the stage for further investigations into the sources of gravitational waves. Another pair of scientists who played a pivotal role in the early understanding of gravitational waves were Joseph Hulse and Russell Taylor. In 1974, Hulse and Taylor discovered a remarkable system, consisting of two neutron stars orbiting each other. This binary system, called PSR B 1913+16, offered the first direct evidence of the existence of gravitational radiation. As the two neutron stars orbit, they slowly lose energy, causing their orbit to shrink over time. According to Einstein's theory of general relativity, this energy loss should be caused by the emission of gravitational waves. Hulse and Taylor carefully measured the shrinking orbit over several years and confirmed that the system was losing energy exactly as predicted by Einstein. This was an indirect confirmation that gravitational waves existed long before the first detection of them. For their work, Hulse and Taylor were awarded the Nobel Prize in Physics in 1993. Their discovery provided compelling evidence that gravitational waves were not just a mathematical curiosity, but a real phenomenon occurring in the universe. This confirmation didn't just support Einstein's theories, it also laid the groundwork for the development of gravitational wave astronomy, making it clear that these waves could be detected if we could only build the right instruments. In parallel with these discoveries, a significant amount of theoretical work was being done by scientists at institutions around the world. One of the most important contributors to the development of gravitational wave theory was Bernd F. Schutz, a physicist at the Max Planck Institute for Gravitational Physics. Schutz played a critical role in creating the mathematical tools necessary to detect gravitational waves. His work on waveform modeling allowed scientists to better understand the signals produced by different astrophysical events, such as black hole mergers and neutron star collisions. These models were essential for guiding the design of the detectors that would eventually observe gravitational waves. Schutz's contributions were part of a broader international effort that spanned multiple decades. As the search for gravitational waves began to take shape, many institutions around the world collaborated on developing the technology necessary to detect these elusive signals. The Max Planck Institute, for example, played a central role in the early theoretical and computational work that informed the development of detectors like LIGO. The involvement of institutions like this was crucial in making gravitational wave astronomy a reality. The importance of international collaboration cannot be overstated. While LIGO, based in the United States, ultimately made the first direct detection of gravitational waves in 2015, many other groups contributed to the effort. In Europe, the Virgo collaboration, which includes scientists from France, Italy and the Netherlands, worked alongside LIGO to improve the sensitivity and accuracy of the detectors. Meanwhile, the Laser Interferometer Space Antenna, LISA, an international project spearheaded by scientists at the European Space Agency, aims to detect low-frequency gravitational waves in space, offering a different perspective on the universe's most extreme events. The collaboration between institutions across different countries highlights the global effort that went into the pursuit of gravitational waves. Scientists, engineers, and researchers from all over the world contributed their expertise to make the detection of gravitational waves possible. And while LIGO's success in 2015 was a landmark achievement, it was also a reminder that scientific progress is rarely the result of a single individual or institution. It is the product of decades of work by teams of dedicated scientists, each building on the discoveries that came before. The importance of these contributions extends beyond just the detection of gravitational waves. The work done by Hulse and Taylor, Bell Burnell, Schutz, and many others has provided us with the tools and knowledge to explore the most mysterious objects in the universe. Black holes, neutron stars, and the forces that govern them have long been some of the most enigmatic subjects in astrophysics. But thanks to the hard work and insights of these key players, we now have a new way of studying these objects, by listening to the faint whispers they leave behind in the form of gravitational waves. And as we continue to improve our ability to detect and analyze these waves, new players will emerge. The study of gravitational waves is still in its early stages, and each new discovery opens up new questions and possibilities. Perhaps, in the future, we will detect gravitational waves from the earliest moments of the universe, or from events we haven't even imagined yet. But whatever comes next, we can be sure that the pioneers who laid the groundwork for gravitational wave astronomy will continue to inspire and inform the next generation of scientists. Their contributions have not only shaped the course of gravitational wave detection, but have also expanded the very boundaries of our understanding of the universe. When we think about gravity, we often imagine a force that pulls objects toward each other, like the way the Earth pulls us down to the ground. But gravity, as we know it today, is much more than that. It's not just a force in the traditional sense, it's the result of the curvature of spacetime, a four-dimensional fabric that makes up the very structure of the universe. Spacetime is a concept that combines the three dimensions of space, length, width, and height, with time, creating a unified continuum. Imagine it like a flexible fabric that stretches across the cosmos, where every object with mass or energy causes a distortion or bend in that fabric. These bends are what we experience as gravity. So, when you drop an apple, it falls not because the Earth is pulling on it directly, but because the Earth has curved the fabric of space-time in such a way that the apple moves toward it. This idea of gravity as space-time curvature was one of the key breakthroughs of Albert Einstein's general theory of relativity, and it fundamentally changed the way we view the universe. This idea of space-time isn't just theoretical, it can be visualized, although it takes a bit of imagination. Picture a stretched rubber sheet and place a heavy ball at the center. The ball creates a depression in the sheet, causing smaller objects to roll toward it. Similarly, planets, stars, and even light bend the fabric of space-time as they move through it. It's a simple yet profound way to understand how gravity works on a cosmic scale, where mass doesn't just pull objects toward it, but warps the very structure of the universe. Now things get even more interesting when we start to consider the work of John Wheeler, a physicist whose ideas on geometrodynamics helped push our understanding of spacetime curvature even further. Wheeler's concept of geometrodynamics suggests that spacetime itself is not just a passive stage on which objects move. Instead, the geometry of spacetime is active, dynamic, and interconnected with the matter and energy within it. In this view, the curvature of spacetime is not something external, but is intrinsically linked to the properties of the objects within it. It's a perspective that makes gravity much more than a force. It turns it into a relationship between the structure of spacetime and the contents of the universe. This idea, which Wheeler helped popularize, became crucial to understanding how objects with massive amounts of energy, like black holes and neutron stars, distort spacetime and generate gravitational waves. When two massive objects collide or spiral toward each other, their extreme energy causes ripples in the fabric of spacetime, which travel outward as gravitational waves. These waves, predicted by Einstein and later confirmed by LIGO, are a direct result of this warped geometry. But what if spacetime isn't just made up of the familiar four dimensions of space and time? What if there are more dimensions hidden from our perception, just waiting to be discovered? This is where the work of physicists like Ed Witten comes into play. Witten is a leading figure in string theory, a theory that proposes that the fundamental building blocks of the universe are not particles but tiny, vibrating strings of energy. String theory suggests that there could be additional dimensions beyond the familiar three of space and one of time. In fact, string theory posits that there could be as many as 10 or 11 dimensions, though most of them are hidden from our view, compacted into incredibly small scales. These extra dimensions could have profound implications for our understanding of gravity and gravitational waves. For instance, some versions of string theory suggest that gravity might not be confined to our familiar 4 dimensions at all. Instead, gravity could leak into these additional dimensions, allowing gravitational waves to interact with them in ways we don't fully understand yet. This opens up a whole new realm of possibilities for how gravitational waves might behave and what they can tell us about the universe's most fundamental properties. When we think about the potential of gravitational waves, we're not just thinking about the ripples created by black holes and neutron stars. We're also considering how these waves might carry information about the very fabric of space-time itself, and whether they could provide clues about the hidden dimensions proposed by string theory. The detection of gravitational waves could be one of the key tools that helps us probe these extra dimensions, offering us a glimpse into a universe far richer and more complex than we can currently perceive. Now, while string theory and extra dimensions are mind-bending ideas, they are not the only unconventional theories about gravity and space-time. One of the most fascinating alternative views comes from physicist Lisa Randall, who has proposed a theory involving warped dimensions. Randall suggests that our universe might be embedded in a higher dimensional space, much like a sheet of paper is embedded in 3-dimensional space. In her theory, the extra dimensions are not tiny and curled up, as in string theory, but instead they could be large and warped, creating a different kind of gravity. In Randall's model, the curvature of space-time would not be uniform as we traditionally think, but could vary depending on the geometry of these higher dimensions. This warped structure could have far-reaching effects on the behavior of gravity, including how gravitational waves propagate through the universe. Randall's work on higher dimensional gravity has provided a fresh perspective on how gravity could operate on both large and small scales, and it has the potential to change how we think about everything from black holes to the nature of dark matter. These higher dimensional theories are still being explored, and they offer intriguing possibilities for the future of gravitational wave astronomy. If gravitational waves can be used to probe the hidden dimensions of the universe, they could provide us with clues that help us unlock some of the biggest mysteries of physics, like the nature of dark matter, or even the secrets of the very early universe, long before the Big Bang. At the heart of these theories, whether it's the idea of space-time curvature, extra dimensions, or the warped geometry proposed by Randall, is the understanding that gravity is not just a force, but a property of space-time itself. As we continue to study gravitational waves and refine our understanding of their sources, we are also deepening our knowledge of the very structure of the universe. And as our instruments become more sensitive, we'll be able to detect waves from even more distant events, allowing us to explore the most extreme and hidden corners of the cosmos. The relationship between gravity, space-time, and quantum mechanics remains one of the most profound questions in physics. While general relativity describes how gravity works on large scales, like galaxies and black holes, quantum mechanics governs the behavior of the tiniest particles in the universe. The challenge for physicists today is to unite these two theories into a single framework that can describe the entire universe, from the smallest quantum particles to the largest cosmic structures. Gravitational waves, with their ability to bridge the gap between the micro and macro worlds, may hold the key to unraveling this cosmic puzzle. As we continue to study gravitational waves, we'll not only learn about the most extreme events in the universe, but also gain insights into the very nature of reality itself. The possibility of hidden dimensions, warped geometries, and the marriage of quantum mechanics with gravity opens up a world of scientific exploration that promises to reshape our understanding of the universe in ways we can only begin to imagine. Gravitational waves, as we've discussed, are ripples in the fabric of space-time itself, travelling across the universe, carrying with them the secrets of distant cosmic events. But what causes these waves? What cosmic events can send such distortions through space-time that they can be detected on Earth, billions of light-years away? To understand this, we must look at some of the most extreme and energetic events in the universe. One of the most significant sources of gravitational waves is the collision of black holes. Black holes are incredibly dense objects where gravity is so strong that not even light can escape. When two black holes orbit each other in a close binary system, their immense gravitational pull causes them to spiral toward one another. As they approach, the space around them becomes more and more distorted, and this distortion is what generates gravitational waves. The merging of these black holes creates a burst of gravitational radiation that travels across the universe, carrying information about the black holes, masses, spins, and other properties. This process, known as a black hole merger, is one of the most energetic events in the universe, and it's a powerful source of gravitational waves. When LIGO detected the first gravitational wave in 2015, it was from such a black hole merger, specifically from two black holes merging approximately 1.3 billion light-years away. Another major source of gravitational waves comes from the violent deaths of massive stars. When a massive star exhausts its nuclear fuel, it can no longer support itself against the force of gravity, causing it to collapse inward. If the star is heavy enough, it will collapse into a singularity, creating a black hole. This process, known as a supernova, is an intense explosion that can release enormous amounts of energy. While most of the explosion is in the form of light and other electromagnetic radiation, the collapse and violent release of energy can also send ripples through space-time. These ripples, gravitational waves, carry information about the properties of the star, such as its mass and the way it collapsed. Supernovae are not as common a source of gravitational waves as black hole mergers, but they provide a valuable signal that scientists are working to detect. Neutron star collisions, too, are a major source of gravitational waves. Neutron stars are the remnants of stars that were not massive enough to become black holes. Instead, they collapse into extremely dense, compact objects made almost entirely of neutrons. When two neutron stars collide, the resulting explosion is incredibly energetic. These collisions create gravitational waves that, much like black hole mergers, carry information about the masses, spins, and other properties of the stars involved. In 2017, LIGO and Virgo detected gravitational waves from the merger of two neutron stars, an event known as GW 170817. This was a groundbreaking discovery because it also coincided with electromagnetic signals, such as gamma-ray bursts, allowing scientists to study the event in multiple ways. The detection of these waves opened up a new era of multi-messenger astronomy, where gravitational waves and light from the same event are studied together. But there's more to gravitational wave sources than just black holes, neutron stars, and supernovae. Theoretical physicists have long speculated about more exotic phenomena that could create gravitational waves, objects and events that might seem almost too strange to be true. One such phenomenon involves the work of physicist Wolfgang Pauli, who proposed ideas in the early 20th century that could help us understand quantum mechanics and gravity. Pauli's exclusion principle, which helps explain why electrons occupy discrete energy levels, was a breakthrough in understanding particle physics. But Pauli also speculated that there could be fundamental interactions between matter and gravity that we don't fully understand yet, especially when it comes to the behavior of matter under extreme conditions, like inside black holes. While Pauli's work was largely focused on the quantum properties of particles, it has implications for how we think about the sources of gravitational waves. For instance, the way matter behaves inside black holes or in other exotic environments could influence the nature of the gravitational waves they produce. Similarly, John Bell, known for his work in quantum mechanics and quantum field theory, offered insights into how quantum properties of matter might relate to the geometry of space-time itself. His work suggests that gravitational waves could reveal not just the properties of objects like black holes, but also the quantum properties of matter that interact with these objects in unexpected ways. If we go further down the rabbit hole of exotic phenomena, we encounter theories about wormholes and the possibility of traversable portals through space-time. A wormhole is a hypothetical tunnel that connects two distant points in space and time, allowing for faster-than-light travel between them. The concept of wormholes comes from the equations of general relativity, and while they remain speculative, they've captured the imagination of physicists and science fiction enthusiasts alike. Kip Thorne, one of the leading scientists in the field of gravitational wave research, has explored the possibility of traversable wormholes in his work on the theoretical aspects of black holes. Thorne's research suggests that if wormholes exist, they might generate gravitational waves of their own. These waves would likely have very different signatures from those created by black hole mergers or neutron-star collisions, and detecting them could provide clues about the structure of space-time itself. While wormholes are still purely theoretical, the possibility of detecting gravitational waves from these exotic objects adds an exciting layer to the study of the universe's most mysterious phenomena. Then, there's the possibility that gravitational waves could help us explore higher dimensions. As we've seen in string theory and related theories, the universe might contain extra spatial dimensions beyond the familiar three. These extra dimensions could be compacted and hidden from view, but their influence on gravity could be detectable. Brian Greene, a leading physicist in string theory, has proposed the idea of the string landscape, where different compactified dimensions could affect the properties of gravitational waves. In such theories, gravitational waves might not just travel through the familiar four-dimensional spacetime, but could also interact with these hidden dimensions in ways we don't yet understand. If gravitational waves can reveal the properties of these extra dimensions, they could unlock one of the most profound mysteries in physics: how to reconcile general relativity and quantum mechanics into a unified theory. As we continue to refine our instruments and methods of detecting gravitational waves, the potential for new discoveries grows. We've already detected waves from the collision of black holes, neutron stars, and supernovae, but these are only the beginning. With the sensitivity of detectors like LIGO, Virgo, and the upcoming space-based LISA mission, we might one day detect waves from even more exotic sources, perhaps from the earliest moments of the universe, or from objects and events we haven't yet imagined. The universe is vast, full of incredible phenomena, and gravitational waves give us a new way to listen to its deepest secrets. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, is a technological marvel. It stands as one of the most significant achievements in modern physics, bringing us closer to understanding the deepest mysteries of the universe. To truly appreciate its role in detecting gravitational waves, we need to explore the engineering brilliance behind its design and the scientific breakthroughs that made it possible. The foundation for LIGO's technology can be traced back to the pioneering work of Albert Michelson and Edward Morley in the late 19th century. Michelson, known for his precision work on measuring the speed of light, teamed up with Morley to conduct an experiment that became famous as the Michelson-Morley experiment. This experiment aimed to detect the ether, a hypothetical substance once thought to fill empty space and carry light waves. The experiment's null result, showing that the speed of light was constant regardless of the Earth's motion, dealt a blow to the ether theory. But more importantly, it opened the door for Einstein's theory of special relativity in the following decade, which revolutionized our understanding of space, time, and light. Michelson's work also laid the groundwork for interferometry, a technique LIGO would later use to measure the tiny distortions caused by gravitational waves. Interferometry itself is at the heart of LIGO's design. The basic idea behind an interferometer is simple. It involves splitting a beam of light into two parts, sending each part along separate paths, and then recombining them to see how they interfere with each other. In the case of LIGO, the interferometer splits a laser beam and sends the two parts down long, perpendicular arms, each 4 kilometers long. These arms are in a vacuum to avoid any environmental interference. When a gravitational wave passes through, it stretches and compresses the space-time between the mirrors at the ends of these arms, causing a tiny change in the length of the arms. This minute difference in distance alters how the laser beams recombine, producing an interference pattern that can be measured. The brilliance of LIGO's design lies in its sensitivity. The distortion caused by a gravitational wave is incredibly small, smaller than the width of a proton, smaller than the diameter of an atom. To measure such tiny changes in length, LIGO's interferometer must be incredibly precise. It is capable of detecting displacements as small as 1/10,000th of the diameter of a proton. This is roughly 1,000th the width of an atom. Achieving this level of precision requires the most advanced technology and a careful approach to minimize any interference or noise in the system. One of the key figures behind the development of LIGO's sensitive interferometric technology is Rainer Weiss, a physicist whose contributions were instrumental in turning the theoretical idea of gravitational wave detection into a practical reality. Weiss, along with others, envisioned how the interferometer could be used to detect gravitational waves, and he was a driving force in the early stages of LIGO's creation. His work focused on improving the sensitivity of the interferometers, ensuring that they could detect the faintest signals from the most distant cosmic events. Weiss's insight into the challenges of noise reduction, alignment, and the need for precise calibration helped make LIGO's extraordinary sensitivity possible. But even with such remarkable technology, detecting gravitational waves was no simple task. LIGO faced many challenges. Gravitational waves are incredibly faint by the time they reach Earth, and the instruments have to contend with a tremendous amount of background noise. Everything from seismic activity to vibrations in the building itself can create spurious signals. These background noises can be mistaken for the gravitational waves the scientists are looking for, so LIGO needed to be capable of distinguishing between these and actual gravitational wave signals. Enter Lance P. Jackson, a physicist whose work on improving the accuracy of signal interpretation became critical in overcoming these challenges. Jackson helped refine the data analysis techniques used by LIGO to filter out the noise and identify real gravitational wave events. His work contributed to the development of algorithms that could isolate the faint signals from the much louder, more chaotic background noise. This ability to separate the signal from the noise was key to LIGO's success. The role of scientists like Jackson working behind the scenes to improve the detection process was crucial in allowing LIGO to make its landmark discoveries. In addition to these challenges, the sheer scale and complexity of LIGO's construction and operation posed significant hurdles. Building a facility capable of measuring such tiny distortions in space-time required advanced engineering, significant funding, and international collaboration. The LIGO project spanned many years and involved teams of scientists, engineers, and technicians from around the world. The detectors were constructed at 2 sites, one in Hanford, Washington, and the other in Livingston, Louisiana, separated by over 2,000 kilometers. This setup allowed LIGO to distinguish between local noise and gravitational waves that were truly coming from outer space, since a gravitational wave would affect both detectors simultaneously, while local disturbances would affect them differently. The significance of LIGO's success cannot be overstated. The first detection of a gravitational wave in 2015 was a momentous event, not just for the LIGO team, but for the entire field of physics. It confirmed a century-old prediction made by Albert Einstein in his general theory of relativity, opening up a new way of observing the universe. By listening to the ripples in spacetime, LIGO allowed us to study cosmic phenomena that were previously invisible to traditional telescopes, like the collision of black holes, the merger of neutron stars, and other extreme events that create gravitational waves. But LIGO's technology isn't just limited to detecting gravitational waves. The precision it offers could be used in other fields of science as well. For example, it could be used to study the very nature of spacetime itself, probing the structure of the universe at the deepest levels. LIGO's ability to detect such tiny displacements could also have applications in other areas of physics and engineering, potentially leading to breakthroughs in technologies that require extreme precision, like advanced sensors or quantum computing. LIGO's success in detecting gravitational waves was the result of decades of hard work, collaboration, and innovation. It's a testament to the power of scientific inquiry, the determination of researchers, and the importance of thinking big. What began as a theory in Einstein's general relativity has now become a cornerstone of modern astrophysics, opening up a new era in our exploration of the cosmos. LIGO has not only proven that gravitational waves exist, but it has also revealed a new way of understanding the universe, one that we can hear, not just see. And with future improvements in sensitivity and the development of space-based detectors like LISA, we may soon be able to explore the universe in ways we've only dreamed of. On September 14th, 2015, a discovery was made that would change the landscape of astrophysics forever. For the first time, scientists detected gravitational waves, ripples in space-time caused by the most violent and energetic processes in the universe. The source of these waves was a black hole merger, an event so powerful that it released more energy in a fraction of a second than the entire observable universe does in its entire lifetime. The signal, named GW15-09-14, was a turning point in science, and it marked the birth of a whole new way of observing the cosmos. The journey to detecting these waves had taken decades of hard work and collaboration. Gravitational waves, first predicted by Albert Einstein as part of his general theory of relativity in 1915, had long been considered too faint to detect. The idea that a gravitational wave could travel across space and distort the very fabric of space-time was fascinating, but no one knew if we would ever have the technology to measure such tiny changes. In fact, for most of the 20th century, gravitational waves were more of a theoretical curiosity than a practical possibility. But thanks to the tireless work of countless scientists and engineers, we eventually reached a point where detection became feasible. The breakthrough came through the Laser Interferometer Gravitational Wave Observatory, or LIGO, which was designed to measure the tiny changes in distance caused by passing gravitational waves. The LIGO detectors, with their 4-kilometer-long arms in both Louisiana and Washington, were designed to detect distortions in spacetime as small as 1/10,000th the width of a proton. This kind of precision was unprecedented. The challenge was enormous, as the faintest vibrations from Earth's environment, seismic activity, traffic, even the subtle movement of the detectors themselves, could easily obscure the tiny signals of gravitational waves. However, the team at LIGO had thought of everything. Through years of planning and refinement, they developed sophisticated methods to eliminate as much noise as possible. By using laser beams split into 2 perpendicular paths, and then recombining them after travelling down these arms, LIGO could measure minute changes in distance caused by the passage of a gravitational wave. The key to its success was its sensitivity, which allowed it to detect the incredibly faint signal from a black hole merger approximately 1.3 billion light-years away. The event that would become GW 150914 was the collision of 2 black holes, each with a mass several times that of the Sun. As these black holes spiraled toward each other, they released massive amounts of energy in the form of gravitational waves. These waves travelled across space, stretching and compressing the very fabric of space-time until they finally reached Earth. The LIGO detectors, which had been waiting for such a signal for years, were ready to catch the wave, and when it came, the signal was unmistakable, a sharp, clean chirp in the data, lasting just a fraction of a second, but carrying a wealth of information about the black holes involved. The signal was the unmistakable fingerprint of a black hole merger, an event that had been predicted by Einstein but never directly observed. The implications of this discovery were profound. For one, it confirmed a key prediction of general relativity, an idea that had been around for over a century but had never been tested directly. Gravitational waves were real, and they were an entirely new way of looking at the universe. Unlike traditional telescopes, which rely on light to observe distant objects, LIGO listens for the sound of spacetime itself. The detection of these waves opened up a whole new dimension of observational astronomy. We could now study the universe through the distortions in spacetime that these powerful cosmic events produce, rather than relying solely on light, which can be blocked, bent, or absorbed by interstellar dust. But LIGO's detection of gravitational waves wasn't just the result of high-tech detectors and years of painstaking work. It was also a triumph of data analysis. The faintness of gravitational waves means that detecting them requires sophisticated algorithms capable of distinguishing the signal from noise. This is where Christopher R. Powell, a physicist and data scientist, played a critical role. Powell pioneered the use of machine learning and advanced data analysis techniques to help sift through the enormous amount of data collected by LIGO. His work involved developing algorithms that could identify the subtle chirp of a gravitational wave in the sea of background noise generated by Earth's natural and artificial activities. Machine learning, a branch of artificial intelligence, allows computers to identify patterns in data without being explicitly programmed to do so. By training these algorithms on simulated data of black hole mergers and other gravitational wave events, Powell and his colleagues were able to teach the computers to recognize the fingerprints of real events. This use of machine learning helped LIGO pinpoint the exact moment that the gravitational wave signal arrived and confirmed that it was indeed a genuine detection. The combination of LIGO's cutting-edge technology and the advanced data analysis techniques pioneered by Powell and others allowed the detection of gravitational waves to be more than just a theoretical triumph. It was a real, measurable achievement. And the implications of this discovery were not just scientific but also cultural. The detection of the first gravitational wave captured the attention of the world. It was front-page news across the globe, marking a significant moment in the history of physics. For the first time, humanity had heard the universe, not with our eyes, but with our ears, as the sound of space-time itself reverberated through the detectors. The discovery also had a profound impact on our understanding of the cosmos. It confirmed that black holes, those mysterious and seemingly invisible objects, could collide and merge in such a way that they released detectable energy in the form of gravitational waves. It also gave us a glimpse into the inner workings of black holes, providing clues about their masses, spins, and even their geometry. Before this discovery, black holes were invisible in every way, except through their gravitational influence on nearby stars. But with gravitational waves, we can now study them directly, even from billions of light years away. The ripple effect of this discovery is still unfolding. Since the first detection, LIGO has detected many more gravitational waves from black hole mergers and neutron-star collisions, each one offering new insights into the nature of the universe. And with the advent of future detectors, such as the Laser Interferometer Space Antenna, or LISA, which will be launched in space, our ability to detect and study gravitational waves will only improve. LISA will allow us to observe gravitational waves at lower frequencies, opening up the possibility of detecting waves from supermassive black holes or even from the very early universe. But the impact of this discovery goes beyond science. It has changed the way we think about the universe itself. We've always looked at the sky through telescopes that gather light, but gravitational wave astronomy is something entirely different. It's a new sense, a new way of experiencing the universe, and it's one that could reveal more about the cosmos than we ever imagined. It's like we've discovered a whole new dimension of space to explore, one that is invisible to the naked eye but full of profound mysteries waiting to be uncovered. The detection of the first gravitational wave was not just a breakthrough in physics, it was a cultural moment, a moment that showed us how far humanity has come in its quest to understand the universe. It opened the door to a new era of exploration, one where we can listen to the universe as well as see it, and perhaps one day unlock its deepest secrets. When we talk about gravitational waves, we're really diving into the heart of Einstein's general theory of relativity, which gives us the most complete understanding of gravity that we have today. But while Einstein's theory may sound like pure physics magic to many, there's an elegant set of mathematical equations behind it that explain how gravity works on the grandest scales of the universe. These equations not only predict the bending of space-time due to mass and energy, but also lay the groundwork for understanding how gravitational waves themselves are created. At the core of general relativity is what's known as Einstein's field equations. These are a set of 10 interrelated differential equations that describe how matter and energy influence the curvature of space-time. In simple terms, these equations tell us how the fabric of space-time is shaped by the presence of mass and energy, and how objects move within that curved space. The form of the equation looks like this: r mu nu minus 1/2 g mu nu r plus g mu nu lambda equals 8 pi g over c to the power of 4. T mu nu now. While this may look like a jumble of symbols, it's actually a very precise way of saying that the curvature of space-time at any point is determined by the amount of mass, energy, and momentum at that point. The term r mu nu represents the curvature of space-time, g mu nu represents the geometry of space-time itself, t mu nu represents the distribution of matter and energy, and lambda represents the cosmological constant, which accounts for the expansion of the universe. The constants g and c are the gravitational constant and the speed of light, respectively. But it's when these equations are applied to dynamic systems, things that are moving, accelerating, or colliding, that we start to see gravitational waves. These waves are the ripples created when massive objects accelerate, causing space-time to stretch and compress. Think of dropping a stone in a pond. The ripples spread out from the point where the stone landed. Similarly, when two black holes merge or two neutron stars collide, they create ripples in space-time that travel outward, and these are what we detect as gravitational waves. The mathematical beauty behind these waves comes in their form, the chirp. A chirp is the characteristic pattern of a gravitational wave signal, which begins with a lower frequency and then rises to a higher frequency as the two objects spiral toward each other. This pattern is predicted by Einstein's equations when the source of the waves, such as a black hole merger, accelerates as it approaches its final collision. This information, embedded in the signal, is what allows scientists to learn about the masses, spins, and other characteristics of the objects involved. When the first gravitational wave detection was made in 2015, scientists were able to match the observed chirp pattern to the theoretical models predicted by Einstein's equations. But this wouldn't have been possible without sophisticated mathematical modeling and data interpretation. This is where the work of physicists like Abhay Mehta became crucial. Abhay Mehta has been a key figure in developing the techniques needed to model the waveforms of gravitational waves and interpret the data from detectors like LIGO. His work in waveform modeling helps scientists predict exactly what kind of signal a given astrophysical event, such as a black hole merger, would produce. Gravitational wave signals are incredibly faint by the time they reach Earth, and distinguishing them from background noise requires the ability to match these faint signals with the models. Mehta's research focuses on creating accurate waveform templates, which are used to identify and analyze gravitational waves once they're detected. These models are vital for ensuring that the data is interpreted correctly and that we can extract the most meaningful information from the waveforms. But general relativity doesn't tell us everything. While Einstein's theory has been extraordinarily successful in explaining how gravity works in our everyday lives and in extreme environments like black holes, there are still unanswered questions about the nature of gravity, especially when it comes to very small scales, such as those governed by quantum mechanics. One area where general relativity is known to struggle is at the quantum level. We have a theory of quantum mechanics that describes the behavior of particles on incredibly small scales. But when it comes to gravity, quantum mechanics and general relativity just don't mesh. This is where alternative theories come into play, such as Lee Smolin's work on loop quantum gravity. Loop quantum gravity is a theory that attempts to quantize gravity, meaning it tries to reconcile general relativity with quantum mechanics. Unlike string theory, which posits extra dimensions and tiny vibrating strings, loop quantum gravity suggests that spacetime itself is quantized. In this view, spacetime is made up of tiny discrete loops that form a network at the smallest scales. Smolin's ideas suggest that, at extremely small scales, gravity may behave in a way that is fundamentally different from how it behaves on the larger classical scales described by Einstein's theory. Gravitational waves, in this framework, could potentially reveal new insights into the nature of spacetime itself. If loop quantum gravity is correct, the gravitational waves we detect may behave in subtle ways that deviate from the predictions of general relativity, particularly at high frequencies or small distances. This would offer a unique opportunity to test the boundaries of both quantum mechanics and general relativity, and could help us uncover whether general relativity is truly complete or if there are deeper layers to the structure of space-time waiting to be discovered. While general relativity provides us with an incredibly accurate picture of how gravity works, the search for a theory of quantum gravity that can encompass both the very large and the very small is one of the biggest challenges in modern physics. Gravitational waves offer a potential way to test these theories. The way gravitational waves propagate through space-time and interact with different structures could give us clues about whether quantum gravity effects are at play, especially when we detect waves from extreme environments like black hole mergers or the very early universe. This is one of the most exciting aspects of gravitational wave astronomy. It's not just about measuring waves, but about probing the very nature of spacetime and testing the limits of our understanding of gravity itself. As we continue to detect more gravitational waves, and as our detectors become even more sensitive, we may begin to see subtle deviations from the predictions of general relativity. If such deviations are found, they could open the door to a new understanding of gravity and the structure of the universe. Gravitational waves have already proven to be a window into some of the most extreme and energetic events in the universe. But as we push the boundaries of our detectors, we may find that they offer much more. They could provide the first clues that lead us to a deeper theory of gravity, one that may eventually unite general relativity and quantum mechanics. The beauty of gravitational waves lies not only in their ability to reveal the cosmos, but also in their potential to revolutionize our understanding of the very fabric of reality. Black holes are some of the most mysterious and fascinating objects in the universe. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. In the classical view, black holes are defined by what's known as the event horizon, the boundary beyond which anything that enters is trapped, with no way out. Yet, despite their profound effects on the fabric of space-time, black holes have remained invisible. We can't observe them directly, because no light can escape to reveal their presence. This is where gravitational waves come into play. While black holes themselves remain hidden, they can still reveal themselves to us through the gravitational waves they emit. These waves are produced when black holes move, merge, or interact with one another, causing distortions in the fabric of space-time. The remarkable thing about gravitational waves is that they travel through space without being blocked or absorbed by matter. This means that for the first time we can study black holes by listening to the waves they create, rather than trying to detect the light or other electromagnetic radiation that they produce, which is impossible due to their nature. The most direct evidence we have of black holes comes from the detection of gravitational waves from black hole mergers. When two black holes orbit each other, they create ripples in space-time, much like the waves on the surface of a pond when you throw a stone into it. As these black holes spiral closer, they begin to emit stronger and more frequent gravitational waves, culminating in a burst of energy when they merge into a single, larger black hole. This merger was first observed by LIGO in 2015, with the detection of gravitational waves from a pair of black holes merging about 1.3 billion light-years away. This event, labelled GW150914, marked the first time that we had directly observed a black hole merger, and it was a landmark moment in the field of astrophysics. Gravitational waves offer us a unique opportunity to study the properties of black holes in ways that would be impossible through traditional means. For example, from the gravitational waves detected during a black hole merger, scientists can infer the masses of the black holes involved, their spins, and even the shape of the event horizon. The precise characteristics of the gravitational wave signal provide a wealth of information about the objects involved. The chirp-like pattern of the wave, which begins with a lower frequency and rises to a higher frequency as the black holes spiral toward each other, allows us to measure how quickly the black holes are moving, how much energy they're emitting, and other key details. These observations offer a direct observable signature of the black holes themselves, but the discovery of black hole mergers through gravitational waves also raises some interesting theoretical questions. For instance, one of the most famous theories regarding black holes was proposed by the physicist Roger Penrose, who introduced the concept of cosmic censorship. Penrose's conjecture, first proposed in the 1960s, suggests that singularities, points where space-time curvature becomes infinite, cannot be observed in isolation. In other words, the singularity at the heart of a black hole should always be hidden behind the event horizon, out of view from any outside observer. This theory, known as the cosmic censorship conjecture, has been a cornerstone of our understanding of black holes. But it also leaves us with a lingering question. What happens inside the event horizon? Gravitational waves provide a way to test this conjecture. When two black holes merge, the data from the gravitational waves can give us insights into the behavior of the event horizon and the singularity at the center of the newly formed black hole. If the singularity is exposed, or if the event horizon behaves in ways that we don't expect, it could challenge Penrose's conjecture and force us to rethink our understanding of black hole physics. The detection of gravitational waves from these mergers may offer clues about the nature of singularities and the structure of spacetime within black holes, an area that has long been shrouded in mystery. In addition to testing Penrose's cosmic censorship conjecture, gravitational wave observations also provide an opportunity to test some of Einstein's predictions about black holes. One of the key predictions of general relativity is that black holes should be completely described by only a few properties: their mass, spin, and charge. This is known as the no-hair theorem, and it suggests that no matter what happens to a black hole, whether it forms from the collapse of a star or from the merger of two black holes, it should always be describable by these three properties alone. Gravitational wave observations give us a powerful tool to test this idea. For example, when scientists detected the gravitational waves from the merger of two black holes in 2015, they were able to measure the masses and spins of the black holes involved. This allowed them to check whether the resulting black hole, the one formed from the merger, had the properties predicted by general relativity. The results were in line with Einstein's theory, confirming that the newly formed black hole could indeed be described by just its mass and spin, with no additional hair or distinguishing features. But not all black hole mergers are straightforward. Theoretical physicist Matthew Choptik has studied what happens when a black hole forms under more dynamic and complex conditions. Choptik's work focuses on the formation of black holes in highly energetic environments, such as during the collapse of a massive star or when two neutron stars merge. In these scenarios, the formation of a black hole can produce violent instabilities that might affect the geometry of spacetime in unexpected ways. Gravitational waves from such mergers could reveal whether these instabilities produce any deviations from Einstein's predictions. In fact, gravitational waves may eventually help us answer one of the most fundamental questions in black hole physics. Do black holes behave exactly as predicted by general relativity, or is there something more to them that we don't yet understand? As LIGO and other gravitational wave detectors continue to collect data, we may uncover subtle deviations from the standard predictions, which could indicate new physics, perhaps related to quantum gravity, the very nature of spacetime, or the behavior of singularities. Black holes, once considered purely theoretical objects, are now a key part of our understanding of the universe. Gravitational waves have transformed the way we study these enigmatic objects, allowing us to observe them directly for the first time. From the mergers of black holes to the behavior of event horizons and singularities, these waves provide us with a window into the most extreme environments in the universe. As we continue to explore the mysteries of black holes through gravitational waves, we may uncover answers to some of the deepest questions in physics, and perhaps reveal a more profound understanding of the nature of spacetime itself. Neutron stars are among the most fascinating objects in the universe. They are the remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own gravity. What's left is an incredibly dense core, made almost entirely of neutrons, packed into a space no larger than a city. These stars are incredibly compact. Just a teaspoon of neutron star material would weigh about 1 billion tons. Their extreme density and strong gravitational fields make neutron stars one of the most exotic and intriguing subjects in astrophysics. When two neutron stars orbit each other in a binary system, they gradually lose energy due to the emission of gravitational radiation. As their orbits decay, they spiral inward, growing closer and closer until they eventually collide in a violent merger. This process is one of the most powerful events in the universe and produces a unique signature in the form of gravitational waves, ripples in space-time that carry information about the stars involved and the physics of the merger itself. These mergers are special for a few reasons. First, neutron star collisions are not only sources of gravitational waves, but also emit a broad spectrum of electromagnetic radiation. This includes gamma rays, X-rays, visible light, and radio waves, which makes them ideal candidates for a new type of astronomical observation called multi-messenger astronomy. Multi-messenger astronomy involves studying the same cosmic event through different types of signals, gravitational waves, electromagnetic radiation, and sometimes even neutrinos. The first successful application of this technique occurred in August of 2017, with the detection of gravitational waves from a neutron star merger, known as GW170817. When LIGO and Virgo, the two gravitational wave observatories, detected the gravitational waves from GW170817, scientists quickly began searching for electromagnetic signals from the same event. They found them. A gamma ray burst, accompanied by X-rays, optical light, and even radio waves, was detected just seconds after the gravitational waves arrived. This was the first time in history that an event had been observed through both gravitational waves and light, opening up a whole new way to study the universe. It was an incredible breakthrough that showed how gravitational wave detectors could be used in tandem with traditional telescopes to gain a more complete understanding of cosmic events. The connection between gravitational waves and electromagnetic signals from neutron star mergers allows us to study the physics of these objects in ways we never could before. For example, from the gravitational waves we can determine the masses of the neutron stars involved, their spins, and how they interact as they spiral toward each other. But the electromagnetic signals add even more detail. They provide information about the material that is ejected in the merger, including the production of heavy elements like gold and platinum. This has led scientists to the realization that neutron star mergers may be the primary source of some of the heaviest elements in the universe. For years, scientists had wondered where elements like gold were created, and now we know that these spectacular cosmic events play a key role in their formation. This is where the work of physicists like Vincenzo Ferrari comes into play. Ferrari has been instrumental in developing the understanding of neutron star mergers through both gravitational waves and electromagnetic observations. His work has helped bridge the gap between these two types of signals, allowing us to better interpret the data and understand the underlying astrophysical processes. By combining gravitational wave data with electromagnetic observations, Ferrari and his colleagues have been able to uncover details about the behavior of neutron stars, their merger dynamics, and the conditions under which they produce heavy elements. Neutron star mergers also offer a unique opportunity to test some of the most fundamental ideas in physics. For example, these events provide a natural laboratory for studying the behavior of matter at extreme densities and pressures. The interior of a neutron star is a place where nuclear matter behaves in ways that are beyond our current understanding. Studying how the gravitational waves from a neutron star merger evolve can give us insights into the equation of state, the relationship between pressure, temperature, and density of the matter inside neutron stars. This is important because the equation of state governs how stars collapse and how they behave under the intense conditions found in black holes and neutron stars. In addition, neutron star mergers also provide a testing ground for some of the most fundamental theories in physics, including Einstein's theory of general relativity. General relativity has been extraordinarily successful in describing gravity, but like all theories, it needs to be tested in a variety of extreme conditions. The high-energy, high-gravity environment of a neutron star merger is one of those conditions. Gravitational wave signals from these events allow us to check whether general relativity holds up in such extreme scenarios or if deviations from its predictions occur. So far, the signals from neutron star mergers have been consistent with Einstein's theory. But as more events are detected, we may uncover subtle differences that could point to new physics. Furthermore, neutron star mergers also provide clues about the very nature of spacetime itself. When two neutron stars collide, they generate intense gravitational waves that distort spacetime in ways we can measure. These distortions carry information about the spacetime geometry in the vicinity of the stars, and offer insights into the behavior of spacetime near these extreme objects. The detailed structure of the gravitational wave signals from neutron star mergers can help scientists probe the fine details of spacetime, testing our understanding of gravity and how it behaves in the most extreme environments. The importance of neutron star mergers goes beyond just the information they provide about astrophysical objects. They also offer a glimpse into the early universe. The detection of these events can help us understand the formation of galaxies, the birth of stars, and the evolution of matter in the universe. Neutron star mergers are some of the most dramatic events in the cosmos, and their study opens up a window into the forces that shape the universe as we know it. As the sensitivity of gravitational wave detectors continues to improve, we can expect to observe more neutron star mergers, and with them, gain an even deeper understanding of the universe. The future of multi-messenger astronomy, combining gravitational waves with electromagnetic signals, will likely lead to even more exciting discoveries. These cosmic messengers, gravitational waves and light, allow us to probe the universe in ways that were once thought impossible. By studying these events, we're not just observing the cosmos, we're unraveling some of the deepest mysteries of nature itself. And in doing so, we are learning more about the universe than we ever could through traditional methods alone. Gravitational waves are cosmic messengers, carrying information about some of the most extreme and mysterious events in the universe. While we have detected a number of these waves from specific events, such as black hole mergers and neutron star collisions, the search for gravitational waves is far from over. The universe is full of other potential sources of these ripples in spacetime, and as our technology improves, so too does our ability to detect these faint signals. One of the most promising sources of gravitational waves is the rotation of neutron stars. These dense remnants of collapsed stars can spin at incredibly high speeds. Some neutron stars rotate hundreds of times per second. As they spin, they can emit gravitational waves, particularly if they are not perfectly spherical. This asymmetry, caused by factors such as magnetic fields or the star's internal structure, can lead to the emission of gravitational radiation. These spinning neutron stars, often referred to as slowly rotating pulsars, are potential targets for future gravitational wave detectors. By detecting the gravitational waves from these objects, scientists could learn more about the inner workings of neutron stars, including their density, structure, and magnetic properties. Another intriguing source of gravitational waves could be white dwarf binaries, systems in which two white dwarfs, the remnants of stars that were not massive enough to become black holes or neutron stars, orbit each other. As these binary systems evolve, they lose energy through the emission of gravitational radiation, causing their orbits to shrink. In some cases, these systems may eventually merge, creating a burst of gravitational waves. These events, although less energetic than black hole or neutron star mergers, still offer valuable information about the properties of white dwarfs and the physics of dense matter. Furthermore, the detection of gravitational waves from white dwarf binaries could help us study the rate of such mergers and better understand the formation of exotic objects like Type 1a supernovae. Primordial black holes, another hypothetical class of black holes, also present a fascinating potential source of gravitational waves. These black holes, unlike those that form from stellar collapses, may have formed in the very early universe, shortly after the Big Bang. They would have masses ranging from tiny substellar objects to supermassive black holes, depending on when and how they formed. While there is currently no direct evidence for primordial black holes, their potential existence provides a compelling reason to continue searching for gravitational waves. If primordial black holes do exist, they could create gravitational waves as they merge or interact with other objects in the universe. Detecting these waves could not only provide evidence for primordial black holes, but also offer insights into the conditions of the early universe, right after the Big Bang. The search for these diverse sources of gravitational waves is not limited to just one observatory or one group of scientists. It is a global effort, with teams of researchers working together to improve our ability to detect these faint signals. One of the key collaborations in this field is the Virgo collaboration based in Italy, which works in conjunction with LIGO to detect gravitational waves. The Virgo detector, located in Cassina, Italy, is similar in design to LIGO, but its location in Europe provides an important complementary advantage to the LIGO detectors in the United States. With both LIGO and Virgo working together, scientists can improve their ability to pinpoint the location of gravitational wave sources and confirm detections more accurately. The role of international collaboration in the search for gravitational waves cannot be overstated. Giorgio Giacomini, a key member of the Virgo collaboration, has contributed significantly to the understanding of gravitational wave signals. His work focuses on improving the sensitivity of the Virgo detector and enhancing the data analysis methods used to interpret the signals. By working together, Virgo and LIGO form a powerful network that can detect gravitational waves with greater precision and accuracy. This collaboration also provides a framework for future international projects that will expand the reach of gravitational wave astronomy. Looking to the future, the next generation of gravitational wave detectors promises to open even more possibilities for discovery. One of the most exciting developments in this field is the Laser Interferometer Space Antenna, or LISA, which is being developed by the European Space Agency and is set to launch in the coming years. LISA will be the first space-based gravitational wave detector, and it will be able to detect lower-frequency gravitational waves that are not detectable by ground-based observatories like LIGO and Virgo. While LIGO and Virgo are sensitive to high-frequency gravitational waves, the low-frequency range is where even more exotic sources of gravitational waves, such as supermassive black hole mergers or the remnants of the Big Bang, can be observed. LISA will be a revolutionary tool in the study of gravitational waves. By positioning its 3 detectors in a triangular formation in space, LISA will be able to detect the stretching and compressing of space-time across vast distances without being affected by the noise and vibrations that interfere with ground-based detectors. This ability to detect lower-frequency waves will open up entirely new avenues of research, including the study of the formation and growth of supermassive black holes, the origins of the universe, and possibly even new physics beyond the standard model. The impact of LISA goes beyond just detecting gravitational waves. It will also provide a unique opportunity to test some of the deepest questions in physics. For instance, LISA's sensitivity to low-frequency gravitational waves may allow us to study how gravity behaves over very large scales, potentially providing clues about the relationship between gravity and quantum mechanics. The ability to study gravitational waves from the earliest moments of the universe, or from the largest black holes, will allow scientists to push the boundaries of our understanding of space-time and the fundamental forces of nature. As LISA and other next-generation detectors come online, the search for gravitational waves will expand beyond the reach of our current technology. These advancements will allow us to probe the universe in new ways, uncovering previously invisible phenomena and answering questions that have fascinated scientists for centuries. From understanding the dynamics of black holes to exploring the earliest moments of the universe, the detection of gravitational waves is opening up an entirely new chapter in the story of cosmic exploration. As we continue to search for gravitational waves, we will uncover more secrets of the universe one ripple at a time, whether from rotating neutron stars, white dwarf binaries, primordial black holes, or the first moments of the cosmos. Each detection brings us closer to understanding the most profound mysteries of space, time, and gravity. The future of gravitational wave astronomy is incredibly bright, and with each new discovery, we come one step closer to answering the biggest questions in physics and cosmology. The discovery of gravitational waves has had a profound effect on modern physics, ushering in a new era of scientific exploration and revealing a universe far more complex and dynamic than we had previously imagined. These waves, which were first detected in 2015 by the LIGO collaboration, provide a completely new way of observing the universe, one that is not limited by light or electromagnetic radiation, but instead listens to the very fabric of space-time itself. Gravitational waves have given us a fresh perspective on some of the most extreme events in the cosmos, like the mergers of black holes and neutron stars, and they are beginning to reshape our understanding of space, time, and gravity. At the heart of these discoveries lies a shift in how we view the universe. For over a century, general relativity, Einstein's theory of gravity, has been the cornerstone of our understanding of how massive objects interact with the fabric of space-time. Gravitational waves, as predicted by Einstein, are an integral part of this theory. But what these waves have revealed goes beyond just confirming Einstein's ideas. They are pushing the boundaries of physics, prompting us to reconsider long-held assumptions about the very structure of space-time and the forces that govern it. One scientist whose work on space-time and the nature of gravity has been deeply impacted by the discovery of gravitational waves is Roger Penrose. Penrose, a Nobel laureate and one of the most influential physicists of our time, has made groundbreaking contributions to our understanding of black holes and the nature of the universe. His work on the cosmic censorship conjecture, which suggests that the singularities inside black holes are hidden from view by event horizons, has long been a cornerstone of black hole theory. But gravitational wave observations, particularly those from black hole mergers, challenge this view in some ways. By studying the waves emitted during these mergers, scientists are gaining new insights into the nature of the event horizon, the singularity, and how they behave under extreme conditions. Penrose's work has always been about looking at the limits of our understanding of space-time. His ideas about the structure of the universe, ideas that seemed abstract and theoretical just a few decades ago, are now being tested and explored in new ways, thanks to gravitational waves. The detection of these waves is not just a confirmation of Einstein's predictions. It is also an opportunity to test the very boundaries of physics, potentially leading to new theories that go beyond general relativity. Another area where gravitational wave research is having a major impact is in our understanding of dark matter and dark energy, two of the most mysterious components of the universe. For years, we have known that most of the matter in the universe does not emit light, and its existence can only be inferred through its gravitational effects. This is what we call dark matter. Similarly, we know that the universe is expanding at an accelerating rate, but the cause of this acceleration is still unclear. This phenomenon is attributed to dark energy. Together, dark matter and dark energy make up about 95% of the universe, yet we know very little about them. One of the theories that could help explain the behavior of these mysterious components is the emergent gravity hypothesis, proposed by physicist Eric Verlinde. Verlinde suggests that gravity is not a fundamental force, but rather an emergent property that arises from the entropic behavior of matter and energy. In his view, gravity could be a macroscopic manifestation of the microscopic properties of space-time, similar to how temperature is an emergent property of the microscopic motions of molecules. If this theory holds true, it could fundamentally change our understanding of gravity and its relationship to dark matter and dark energy. Gravitational waves could play a key role in testing and refining Verlinde's hypothesis. The way gravitational waves behave and propagate through space-time could provide valuable clues about the nature of gravity and whether it truly is an emergent property. If gravitational waves deviate from the predictions of general relativity in ways that cannot be explained by traditional models of gravity, it could be a sign that emergent gravity or some other new theory is at play. In this sense, Gravitational wave astronomy could offer a powerful tool for probing the deepest mysteries of dark matter and dark energy. In addition to testing our understanding of gravity, gravitational wave discoveries are also challenging the standard model of particle physics. The standard model, which describes the behavior of fundamental particles and the forces that govern them, has been remarkably successful in explaining a wide range of phenomena. However, it is known to be incomplete. For example, it does not account for gravity, nor does it explain the properties of dark matter or dark energy. One of the great goals of modern physics is to reconcile the standard model with general relativity, ultimately leading to a unified theory of everything. Gravitational waves could provide key insights into this pursuit. The study of how gravitational waves behave at the quantum level could help us understand the relationship between gravity and quantum mechanics, two pillars of modern physics that have so far resisted unification. Gravitational waves may reveal new quantum gravity effects, showing how space-time behaves on the smallest scales. These observations could offer clues about the nature of space-time itself, such as whether it is fundamentally smooth or discrete, and whether the principles of quantum mechanics apply to gravity in the same way they apply to other forces. One area where gravitational waves could challenge the standard model is in their potential connection to quantum entanglement. Entanglement is a phenomenon in which two particles become linked in such a way that their properties are correlated regardless of the distance between them. This phenomenon is central to quantum mechanics, but it has never been fully understood in the context of gravity. Gravitational waves, especially those from extreme events like black hole mergers, could help scientists explore whether quantum entanglement plays a role in the behavior of space-time, offering a new window into the relationship between quantum mechanics and gravity. The detection of gravitational waves has already revolutionized the way we study the universe, and its impact on modern physics will only continue to grow. Each new discovery adds to our understanding of the universe's most extreme and mysterious phenomena, from black holes to dark matter. As we refine our detectors and develop new technologies, we may uncover even deeper connections between gravitational waves and the fundamental forces of nature. These discoveries could ultimately lead to the unification of general relativity and quantum mechanics, transforming our understanding of the universe at its most fundamental level. Gravitational waves are not just a confirmation of Einstein's predictions, they are a gateway to new physics, offering us a deeper understanding of gravity, space-time, and the very fabric of reality itself. The journey is just beginning, and the possibilities for discovery are endless. As we continue to explore the cosmos through the lens of gravitational wave astronomy, we may one day unlock the greatest secrets of the universe, revealing a more complete and unified picture of the nature of space, time, and everything in between. The future of gravitational wave astronomy is brimming with exciting possibilities, holding the potential to uncover new dimensions of the universe and revolutionize our understanding of the cosmos. While we've made remarkable strides since the first detection of gravitational waves in 2015, we're still only scratching the surface of what these ripples in space-time can teach us. As our detectors improve and new technologies emerge, the scope of gravitational wave research is set to expand, opening up new frontiers in our quest for knowledge. One of the most intriguing possibilities for the future is the detection of gravitational waves from the very first moments of the universe, the Big Bang itself. This is an exciting prospect because it would provide us with a glimpse into a time when the universe was incredibly young and in a state of extreme density and energy. During the first few moments after the Big Bang, the universe underwent rapid expansion in a process known as cosmic inflation. Gravitational waves from this early period would carry with them information about the very origins of the universe and the fundamental forces that shaped its evolution. Detecting these primordial gravitational waves would be like listening to the echoes of the birth of the cosmos, offering insights into the earliest moments of space-time itself. While these waves from the dawn of the universe are currently beyond the reach of our existing detectors, future advancements in technology could bring them within our grasp. For instance, the Laser Interferometer Space Antenna, or LISA, which is set to launch in the next decade, is a space-based gravitational wave detector that will be sensitive to lower-frequency gravitational waves. LISA's ability to observe these lower frequencies could provide us with a clearer view of the waves generated by inflation, potentially allowing us to detect them for the first time. If we succeed in detecting these early gravitational waves, it could mark one of the most profound discoveries in physics, shedding light on the very origins of space and time. As we venture further into the realm of gravitational waves, we are also moving closer to merging two of the most fundamental pillars of modern physics: quantum mechanics and general relativity. These two theories describe the universe at vastly different scales. Quantum mechanics governs the behavior of the smallest particles, while general relativity explains the behavior of massive objects and the structure of space-time on the grand scale. But the two theories have never been fully reconciled, and much of modern physics is devoted to finding a way to unify them into a single, coherent framework. Gravitational waves could play a central role in this pursuit, offering a unique opportunity to study the behavior of gravity at both the macroscopic and microscopic levels. One of the scientists at the forefront of this effort is Carlo Rovelli, whose work on quantum gravity seeks to merge the principles of quantum mechanics with the fabric of spacetime described by general relativity. Rovelli's theory, known as loop quantum gravity, suggests that spacetime itself is quantized, meaning that space and time are made up of discrete chunks rather than being continuous. This idea challenges our traditional understanding of spacetime as a smooth, unbroken continuum. If gravitational waves behave in ways that differ from the predictions of general relativity, it could provide a glimpse into the quantum nature of spacetime and offer clues about the fundamental structure of the universe. Rovelli's ideas, and the potential for new physics emerging from the study of gravitational waves, could help bridge the gap between the quantum and gravitational worlds. The detection of gravitational waves, particularly those from extreme events like black hole mergers, could reveal subtle deviations from general relativity that might point toward new quantum gravity effects. These effects could be the key to understanding how gravity works at the quantum level, potentially leading to a unified theory of everything that encompasses both the forces of quantum mechanics and the curvature of space-time. As we continue to push the boundaries of gravitational wave research, we can also look forward to new innovations in detection technology. One such innovation is the Kagura detector, located in Japan. Kagura is a next-generation interferometer that is similar to LIGO and Virgo, but is designed to be even more sensitive, especially to low-frequency gravitational waves. What sets Kagura apart is its use of cryogenic mirrors, which help reduce thermal noise and improve sensitivity. Kagura's unique design, combined with its location in a region with relatively low seismic activity, makes it an important addition to the global network of gravitational wave observatories. As Kagura becomes fully operational, it will help us further refine our measurements of gravitational waves and provide new insights into the most extreme cosmic events. These advances in gravitational wave detection are not just about improving sensitivity, they're about expanding our reach across the universe. With detectors like LIGO, Virgo and Kagura, we've already made significant strides in detecting gravitational waves from relatively nearby events, such as black hole mergers. But as we expand our detectors and improve our technology, we will be able to probe deeper into the universe. Gravitational waves could allow us to study the formation of galaxies, the collision of supermassive black holes, and even the remnants of the Big Bang itself. Each new detection brings us closer to answering some of the biggest questions in cosmology, from the nature of dark matter and dark energy to the origins of the universe. One of the most exciting possibilities for the future of gravitational wave astronomy is the potential for multi-messenger astronomy. This approach involves combining data from multiple observatories that detect different kinds of signals: gravitational waves, electromagnetic radiation, and even neutrinos, to gain a more complete picture of cosmic events. The merger of two neutron stars in 2017, for example, was a landmark event in multi-messenger astronomy. The gravitational waves from the merger were detected by LIGO and Virgo, while electromagnetic signals, including gamma-ray bursts and visible light, were observed by telescopes around the world. This unprecedented combination of signals allowed scientists to study the same event in multiple ways, offering a more detailed understanding of the physics behind the merger and the creation of heavy elements like gold. As gravitational wave detectors become more sensitive and more widespread, we can expect to see even more multi-messenger observations. LISA, for example, will be able to detect gravitational waves at lower frequencies, while traditional telescopes will continue to observe the electromagnetic spectrum. Together, these different types of observations will allow us to study the universe in ways that were once thought impossible, providing insights into the most distant and violent events in the cosmos. The future of gravitational wave astronomy is incredibly exciting, with new discoveries on the horizon. As we continue to improve our detectors, merge quantum mechanics with relativity, and expand our understanding of the universe, gravitational waves will undoubtedly play a central role in answering some of the deepest questions in physics. From exploring the first moments of the Big Bang to testing the nature of gravity itself, the possibilities are endless. Gravitational waves have already transformed the way we observe the universe, and as our technology evolves, they will continue to unveil the hidden wonders of the cosmos. Gravitational waves are offering us a unique and powerful way to look into the distant past, reaching all the way back to the earliest moments of the universe. These ripples in space-time, traveling across billions of light years, carry information not just about the most violent and energetic events we can observe today, but also about the birth of the universe itself. By studying these waves, we can learn about periods in cosmic history that were previously out of reach to us, including one of the most profound moments in the evolution of the universe, the period known as inflation. The Big Bang, which marks the birth of our universe, was followed by a period of rapid and exponential expansion. This period, which took place in the very early moments after the Big Bang, is referred to as inflation. During inflation, the universe expanded at a mind-boggling rate, growing by a factor of at least 10 to the power of 50 in a fraction of a second. This expansion set the stage for everything that came afterward, setting the overall structure of the cosmos, distributing matter, and creating the conditions for the formation of galaxies, stars, and eventually planets. Inflation is a key part of the standard model of cosmology, but it has never been directly observed. Scientists theorize that this rapid expansion stretched quantum fluctuations in the fabric of space-time, which were tiny, microscopic distortions in the very structure of the universe. These fluctuations are thought to have been imprinted on the universe's structure, creating subtle ripples that traveled across space-time as the universe continued to expand. This is where gravitational waves come in. One of the most exciting possibilities of gravitational wave research is the potential to detect these primordial waves, waves from the very early universe that were generated during inflation. These primordial gravitational waves would be incredibly faint, but they would carry with them critical information about the universe's earliest moments, offering us a glimpse into the very birth of space-time itself. If we could detect these waves, it would not only confirm the theory of inflation, but also help us answer some of the most fundamental questions about the early universe. The search for these primordial gravitational waves is one of the most exciting frontiers in modern physics. Detecting these waves would allow scientists to probe a period of time that is otherwise invisible to us. Unlike light, which gets scattered or absorbed by matter as it travels through space, gravitational waves can travel freely through the universe, carrying with them a record of the events that created them. As a result, gravitational waves provide a direct and unaltered view of the universe's infancy, offering a new window into a time that we could never reach using traditional telescopes or other instruments. The theory of inflation itself was proposed by physicist Alan Guth in 1980, and it has since become a cornerstone of our understanding of the early universe. Guth's idea was that during the first fraction of a second after the Big Bang, the universe expanded incredibly rapidly, driven by a mysterious energy field. This expansion would have stretched any quantum fluctuations in space-time, imprinting them on the fabric of the universe. These imprinted fluctuations, now thought to manifest as primordial gravitational waves, would carry a signature of this extraordinary expansion. If we were to detect these primordial gravitational waves, it would not only provide direct evidence for inflation, but also allow us to study the properties of the energy field responsible for it. This energy field, known as the inflaton, is thought to have played a crucial role in driving inflation, but its properties remain largely unknown. Gravitational waves from inflation could reveal details about the inflaton field, such as its potential energy and how it interacted with the universe's early particles. This would help us answer some of the deepest questions about the origins of the universe, and even potentially offer a window into the nature of dark energy, the mysterious force thought to be driving the accelerated expansion of the universe today. While the detection of these primordial waves is still beyond our current capabilities, the technology is advancing rapidly. Upcoming missions like the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector set to launch in the next decade, could play a crucial role in detecting lower frequency gravitational waves that are beyond the reach of ground-based detectors like LIGO. LISA will be able to detect waves from much farther back in time, including those from the earliest moments of the universe, opening up new possibilities for studying inflation and the origins of the cosmos. In addition to primordial gravitational waves, the detection of gravitational waves could also help us probe some of the more mysterious aspects of spacetime itself, such as the nature of dark matter and dark energy. These elusive components make up the vast majority of the universe's content, yet we have little understanding of what they are or how they interact with ordinary matter. The study of gravitational waves, especially from extreme cosmic events like black hole and neutron star mergers, could shed light on how these unknown substances influence the universe's evolution. Gravitational wave astronomy could also challenge our current models of spacetime. For example, the detection of primordial gravitational waves from the early universe could offer insights into the nature of quantum gravity, a theory that seeks to unify the principles of general relativity with those of quantum mechanics. The quantum fluctuations that generated inflation are closely related to the quantum properties of spacetime, and studying the way gravitational waves behave could offer clues about how these two realms of physics interact. Gravitational waves could help us probe the very structure of spacetime at the smallest scales, potentially offering evidence for a more complete theory of gravity. Looking ahead, the future of gravitational wave research holds even more exciting possibilities. As our detectors become more sensitive and more sophisticated, we will be able to detect waves from even more distant and extreme sources. This will allow us to continue exploring the universe's most violent and energetic events, such as the collision of supermassive black holes or the birth of galaxies in the early universe. Each new discovery will bring us closer to understanding the forces that govern the cosmos and offer a deeper understanding of how the universe came to be. In many ways, gravitational wave research is still in its infancy. We've only begun to scratch the surface of what these waves can teach us about the universe. The discovery of primordial gravitational waves, for example, would mark a new era in cosmology, allowing us to look back to a time when the universe was no more than a fraction of a second old. It would provide us with a direct, unfiltered view of the origins of spacetime and the forces that shaped the early cosmos. As our detectors improve and our understanding of gravity and spacetime evolves, gravitational waves will continue to be a key tool in our quest to uncover the deepest secrets of the universe. Spacetime, this invisible fabric that binds the very structure of the universe. It's a concept that has captivated scientists, philosophers, and thinkers for centuries. But what exactly is it? How does it behave? And most importantly, how can we explore it? These are the questions that have driven much of modern physics, and in recent years, gravitational waves have become a revolutionary tool in helping us answer them. At its core, spacetime is the four-dimensional continuum that combines the three spatial dimensions, length, width, and height, with the dimension of time. In the classical view, we tend to think of space and time as separate entities. But in Einstein's theory of general relativity, space and time are intricately woven together, forming a single fabric. Massive objects like stars and planets cause this fabric to curve, and it is this curvature that we experience as gravity. Instead of a force pulling objects toward each other, as was once thought, gravity is now understood as the result of the bending of spacetime itself. But spacetime isn't a static entity, it's dynamic. It can be warped and stretched by moving objects, particularly those with a lot of mass or energy. And this is where gravitational waves come in. Gravitational waves are ripples in the fabric of spacetime itself. They are created when massive objects accelerate, disturb, or collide in space, sending out waves that travel outward, carrying information about the event that created them. These waves are incredibly faint by the time they reach Earth, but they carry with them profound insights into the nature of spacetime. When a gravitational wave passes through space, it stretches and compresses the distances between objects, distorting the very geometry of spacetime. The fact that we can now detect these minute distortions means that we have a unique tool to probe the fabric of spacetime itself in ways that were once unimaginable. It's as though we've been given a new sense, one that allows us to feel the very texture of spacetime, even when it's stretched over vast cosmic distances. The potential of gravitational waves goes far beyond simply confirming Einstein's theory of gravity. They offer us the ability to explore the most extreme environments in the universe. black holes, neutron stars, and the dense energetic regions around them. By studying the waves they create, we can learn about the underlying properties of space-time in these extreme conditions, and this has profound implications for our understanding of the cosmos. The deep connection between gravitational waves and quantum physics is one of the most exciting aspects of this field. While general relativity has been incredibly successful at describing gravity on large scales, it does not integrate with quantum mechanics, the theory that describes the behavior of particles at the smaller scales. Quantum mechanics has been immensely successful in explaining the forces and particles that govern the microscopic world, but it doesn't account for gravity. On the other hand, general relativity excellently describes how gravity operates in the macroscopic world, but it doesn't fit well with the principles of quantum theory. Gravitational waves offer a unique opportunity to bridge this gap. Gravitational waves are not just a phenomenon described by general relativity. They also have a quantum nature. They are fluctuations in space-time that, at their core, are governed by quantum principles. This makes them a potentially valuable probe for testing the relationship between quantum mechanics and gravity. One of the most influential physicists to delve into this intersection was Stephen Hawking, who made groundbreaking contributions to our understanding of black holes and the nature of space-time. Hawking's work on black hole thermodynamics revealed that black holes are not entirely black, but emit radiation, a phenomenon now known as Hawking radiation. This radiation, while not directly observable yet, suggested that black holes could slowly lose mass over time. More importantly, Hawking's theories sparked new discussions about the quantum properties of space-time itself. When it comes to gravitational waves, Hawking's theories can help us think about how quantum effects might manifest in space-time. If gravitational waves are, at their core, a quantum phenomenon, they might allow us to observe quantum gravity effects in action, especially in the extreme environments near black holes. We could potentially witness how space-time behaves at the smallest scales, where quantum effects dominate. This could lead to new insights into the very nature of space and time, insights that would be impossible to obtain with traditional observations of light or matter. Hawking's work on black holes, particularly his thoughts on the information paradox, has led to new theories about the fundamental structure of space-time. According to general relativity, nothing can escape a black hole once it crosses the event horizon. But quantum mechanics suggests that information cannot be lost. This apparent contradiction remains one of the most pressing questions in theoretical physics. Gravitational waves could provide a way to test theories related to this paradox. As black holes merge and gravitational waves are emitted, scientists may be able to determine whether information is preserved in the waves, offering a potential clue to the quantum nature of black holes and space-time. Another physicist who has made significant contributions to our understanding of the quantum nature of space-time is Carlo Rovelli, who developed the theory of loop quantum gravity. Rovelli suggests that space-time is not smooth and continuous, as general relativity describes it, but instead is made up of tiny, discrete chunks, a kind of quantum foam. This radical idea challenges our traditional view of space and time and has profound implications for the study of gravitational waves. If space-time is quantized, as Rovelli suggests, the behavior of gravitational waves could reveal whether space-time behaves as a smooth continuum or whether it is, in fact, discrete at the smallest scales. Detecting gravitational waves from the most extreme environments, such as the interiors of black holes or the early moments of the universe, could help us test these theories and shed light on the quantum structure of space-time. Gravitational waves are not just a tool for understanding gravity and quantum mechanics. They also enrich our understanding of the cosmos itself. These waves allow us to observe cosmic events that are invisible through traditional means, such as the collision of black holes or the merger of neutron stars. By studying the waves these events generate, we can learn more about the properties of the objects involved, such as their masses, spins, and the dynamics of their interactions. In turn, this provides new insights into the processes that govern the evolution of galaxies, the formation of stars, and the dynamics of cosmic structures. Moreover, gravitational waves have the potential to challenge and expand our understanding of space-time itself. While Einstein's theory of general relativity has stood the test of time in many ways, gravitational waves offer a way to probe the very fabric of space-time under extreme conditions. By observing how gravitational waves behave in these extreme environments, we may uncover new physics that goes beyond general relativity. It's as though we're pushing the boundaries of our understanding, seeking to learn more about the fundamental structure of the universe, and gravitational waves are the key that may unlock these mysteries. In the coming years, as our detection capabilities improve and we continue to observe more gravitational waves, we may uncover answers to some of the most profound questions in physics, whether it's understanding the quantum nature of space-time, exploring the origins of the universe, or testing the limits of general relativity. Gravitational waves are providing us with a powerful new tool for probing the cosmos. The nature of space-time, once a concept relegated to theoretical models, is now within our grasp, and with gravitational waves, we have a new way of experiencing the universe itself. Gravitational waves have opened a whole new frontier in our understanding of the cosmos, giving us a fresh way to explore the universe. For centuries, we've looked to light and electromagnetic radiation as our primary means of observing distant objects, from stars and galaxies to the faint glow of the cosmic microwave background. But gravitational waves have shown us that there's much more to the universe than we can see with our eyes, or detect with traditional telescopes. These ripples in space-time are offering us a glimpse into the universe's most extreme and enigmatic phenomena, and the potential for discovery is boundless. While we've already detected gravitational waves from some of the most well-known sources, like the mergers of black holes and neutron stars, there's an entire universe of unknowns out there that may also be leaving their mark on space-time. One of the most exciting possibilities is the idea that gravitational waves could help us search for some of the most elusive components of the universe: dark matter and dark energy. These two mysterious entities make up approximately 95% of the universe's total mass energy content, yet we know almost nothing about them. Dark matter is thought to be a form of matter that doesn't interact with light or other forms of electromagnetic radiation, making it invisible to telescopes. Its presence is inferred only by its gravitational effects on galaxies and galaxy clusters. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe, but its true nature remains one of the most profound mysteries in cosmology. While gravitational waves have already provided insights into the nature of gravity and space-time, they may also hold the key to understanding dark matter and dark energy. One possibility is that gravitational waves could reveal new forms of dark matter. Some theories suggest that dark matter could consist of ultralight particles, such as axions, which are hypothesized to be extremely weakly interacting and would not emit or absorb light. These particles might create tiny fluctuations in space-time that could be detectable as low-frequency gravitational waves. Similarly, gravitational waves might also offer a way to probe the effects of dark energy on space-time. Some models suggest that dark energy could create distortions in space-time that leave an imprint on the gravitational wave signals traveling through the universe. By studying these signals, scientists may be able to test whether these effects are real and gain new insights into the nature of dark matter and dark energy. As gravitational wave detectors become more sensitive, the potential for discovering these hidden cosmic phenomena grows. The recent progress in the field of gravitational wave astronomy is the result of decades of work by scientists and engineers around the world. One such researcher pushing the boundaries of this field is Rebecca C. Barone, whose work has focused on enhancing the sensitivity of gravitational wave detectors and exploring new ways to interpret the data they collect. Barone's efforts have helped improve the accuracy of the measurements, which is critical when detecting such faint signals. Her work is part of a larger international effort where the contributions of many scientists working in collaboration continue to drive forward our understanding of gravitational waves. The work of scientists like Barone is crucial in pushing the frontiers of gravitational wave astronomy. As the sensitivity of detectors like LIGO, Virgo, and the upcoming LISA continues to improve, we will be able to detect even fainter and more distant gravitational wave signals. This opens up a world of possibilities, from observing the most distant black hole mergers to detecting gravitational waves from the earliest moments of the universe. With each new observation, we're able to learn more about the most extreme objects and events in the universe, from black holes to neutron stars, and potentially even uncover new phenomena that we haven't yet imagined. One of the most exciting prospects for the future is the possibility of detecting gravitational waves from the formation of the first stars and galaxies in the early universe. These signals could help us probe the very beginnings of the cosmos, revealing the processes that took place during the formation of the first structures after the Big Bang. This is a key question in cosmology, and gravitational waves could provide the first direct evidence of these early cosmic events. We might also be able to detect gravitational waves from the formation of the first black holes, or even primordial black holes, which are thought to have formed in the very early universe, but have not yet been directly observed. As the field of gravitational wave astronomy evolves, new theories and questions will emerge. For example, the discovery of gravitational waves from previously unknown sources could challenge our current models of the universe, leading to new theories of gravity, quantum mechanics, and space-time. The detection of gravitational waves could also help us test the fundamental principles of physics, including Einstein's theory of general relativity, and explore new ideas that go beyond the standard model of particle physics. The potential for breakthrough discoveries is immense, and as our tools for detecting gravitational waves improve, so too does our ability to explore the deepest and most elusive aspects of the cosmos. The pursuit of understanding the universe through gravitational waves is an ongoing and limitless journey. Just as the discovery of light and electromagnetic radiation opened the door to understanding the universe in the last century, gravitational waves are set to do the same in this one. With the continued development of new detectors, the refinement of data analysis techniques, and the collaboration of scientists across the globe, we are embarking on a new era of cosmic exploration. The questions we can now ask about dark matter, dark energy, the nature of gravity, and the origins of the universe are deeper than ever before, and each answer brings us closer to understanding the grand and complex workings of the universe. In the coming decades, as we detect more gravitational waves from increasingly distant and exotic sources, the discoveries will only become more profound. We are living in a time of unprecedented scientific discovery, and the search for cosmic mysteries through gravitational waves will continue to push the boundaries of knowledge, revealing secrets of the universe that were once thought to be forever beyond our reach. Whether we are uncovering the mysteries of dark matter, probing the earliest moments of the universe, or testing the very fabric of space-time itself, the pursuit of gravitational wave astronomy promises to unlock some of the greatest secrets of our cosmic existence.